In this video I will talk about non-parametric estimation methods for value at risk. So what it means is that we estimate VAR without assuming any distribution for the data. Right, I will consider 4 different methods. Start with the first one, which is called the historical. It's called the historical method. All right. Now suppose these are the losses. Okay, and we want to estimate VAR. Okay, so the first thing we must do is to arrange the data from the smallest to the largest. So it means, so suppose this is the smallest, I'm going to denote it by this. Suppose this is the second smallest, denoted by this, and suppose this is the largest. So you have these inequalities. Right. So this is the smallest data value, the smallest loss, right? And this is the largest loss, right? Okay, so given this, the historical method says the estimator for VAR, right, is given by the ith smallest data value if P is the probability, lies in the interval from I minus 1 divided by n to I divided by n. So includes this I divided by n but excludes I minus 1 divided by n. Right. Let me just do one example. Example 1 on this. Now suppose the data are as follows. Suppose you have the data, say plus 5, minus 2, 3, 0, 1. Suppose these are just numbers I just took randomly. Now the first thing is to arrange the data from the smallest, which is this one. Minus 2 is the smallest, then 0, then 1, then 3, then 5. Okay. So this is your x1 in brackets, this is your x2 in brackets, this is your x3 in brackets, and this is your x4 in brackets, and this is the largest, which is x5 in brackets. Okay. Now suppose you want to find VAR at 0.4. So your P is equal to 0.4. So if p is 0.4 and you suppose you take I to be 2, then your n is 5. So 2 minus 1 divided by 5 will be 0.2, right? And I is 2 divided by 5 will be 0.4. So this will be equal to 0 because the reason is because 0.4 belongs to the interval from 1 divided by 5 to 2 divided by 5. Okay? And suppose now you want to find, say, var is 0.9. Right, this will be equal to 5, right? Because, okay, 0.9 belongs to the interval 4 divided by, sorry, I is 5, yeah, 4 divided by 5, which is 0.8, to 5 divided by 5, which is 1. All right, so in this case, your I is equal to 5, right? In this case, your I is equal to 2, right? So you pick the second smallest. Because I equal to 5 here, you pick the largest, which is 5. All right, hope this is clear. So that's the first method, the historical method. The second method, is known as the bootstrap. Bootstrap is a popular technique in statistics. Used in every area of statistics, bootstrap is popular. So let me bootstrap is due to Brad Efron. He's a professor at Stanford University in California, right? Now suppose once again that x1 to xn are the losses, right? So in this method, according to this method, you need to first compute the empirical CDF of the data. Which is given by this formula here. Right, this is the empirical CDF of the data. Well, I denotes the indicator function. Okay, I think I defined what an indicator function is before in this course some time ago, right? Now, what the empirical CDF, like if you try to try to plot the f of x, f hat of x versus x, it will look something like this. So give me some time before I draw it. Okay, suppose this is the smallest data, this is second smallest, and this is the largest, right? Okay, and the graph will, if I use a red color, it will start at 0, right? And it will end at 1. Now, it starts at x, at the smallest value, it'll jump by a unit, right? And it will stay there until it hits the second smallest. Then it will jump once again by a unit, right? And then it will stay until it hits the third smallest, right? And then it will jump by another unit, and so on, until when you hit the largest data point, it will become exactly equal to 1, right? So it will be equal to it will become exactly equal to 1 at the largest data point. So every time like when it hits the smallest data point, it increases by 1 over n, and it increases by another 1 over n, making it 2 over n, right? And so on until when it hits the largest data point, it becomes equal to 1, right? So this is known as the empirical CDF, or cumulative distribution function. There are programs in the R software. There are programs in the R software for computing the empirical CDF, right? Okay, now the procedure for computing var is as follows. So the procedure is as follows. The first step, all right, is to simulate b, capital B is an integer, right, is to simulate b independent random samples, each of size n from f hat. And as I said, there are methods for doing this in the R software. The second step is to Right, compute the estimate for var by the historical method, which I described earlier, for each of the B samples. So resulting in let me give you some notation. Say let this denote the estimate for var for the first sample, and this denote the estimate for var for the second sample, and so on until you have B samples. So let this denote the estimate for var for the bth sample. And the final step is to take the overall estimator for var, right, as the mean of the B estimates, capital B, okay, or the median of the B estimates. All right. So this completes the procedure for the Bootstrap method for estimating value at risk, right? So simulate B independent samples from the empirical CDF, and then compute var by the historical method for each of them, each of the B independent samples, and finally take the final estimate for var either as the mean or the median of the B estimates. Right. Now, that's the second method. The third method I'm going to talk about is known as the jackknife method. It's very similar to the Bootstrap method. Number 3. Okay, suppose once again that x1 to xn are the data on losses. All right, the procedure is as follows. The procedure for computing var. So the first step is to compute var by the historical method, for the data set x2, x3 up to xn. So you see here I have left out the first data point x1, and let this notation denote the estimate. The second step is to compute var by the historical method, for the data x1, x3 up to xn. So you see here we have removed the second data point. Let this denote the estimator. Right, and you repeat this procedure until the final step, which is compute var by the historical method for the data x1, x2 up to xn minus 1. So here we have removed the last data point xn, and let this notation denote the estimate. Okay. So at the end of this steps, we have n different estimates for var. All right. The final step is as follows: you take the overall estimator for var as follows. As the mean of the n estimates, right? Or you take them as the median of the n estimates. All right, so this completes the jackknife. So it's very similar to the bootstrap method, except here at each iteration you remove one data at a time. Right, so you have n estimates left, and in the final step you take the mean or the median of the n estimators. All right, so that's method number 3. Now, the final method number 4, is known as the kernel method. You may recall that, I don't know whether you've done kernel estimation before, but it's a popular method in statistics, kernel estimation. Right, the kernel estimation it used to produce smoothed versions of the distribution of the data, right? Whereas the empirical CDF I showed you earlier, it does not produce smooth versions of the data. If you may recall the picture I showed you earlier, if I can find it, here we are. This is the picture of the empirical CDF I showed you earlier. The diagram that you have here is not a smoothed version. It's like a step ladder. going up, up and up in every step. So whereas kernel estimation, it produces a smooth version of the CDF of the data. So the kernel CDF, the kernel CDF of the data is as follows. This is given by the following formula: f hat equal to 1 over n times the sum from 1 to n of capital G x minus xi divided by h, where h is the bandwidth. I will explain what that is in a minute. Bandwidth. And G is given by this expression, integral from minus infinity to x of ku du, and k is known as the kernel PDF. Kernel PDF, right? And it's usually chosen as the standard normal PDF, which is, I'm sure all of you know that the density of the standard normal distribution, which is this. Okay. Now, this is the formula for the kernel CDF. So unlike the empirical CDF, which I talked about earlier, this kind of produces a smooth version of the CDF of the data. H is it controls the bandwidth. In other words, it controls how smooth the CDF will be, how smooth the kernel CDF will be, right? So the larger the value for H, the smoother the estimate will be, estimate of the CDF. The smaller the value for H, it will be less smooth the CDF will be. G is given by this, and K is the kernel PDF, usually chosen as this. So let me write something about the H. So H controls the smoothness of the kernel estimator, kernel CDF, right? Larger the value of H, more smooth f hat will become. Okay, right. All right, so this is all about the kernel CDF. Now, the procedure for computing var is as follows. The var so the estimator for var under the kernel method can be computed as, there are two different ways. One is as the root of the equation that f hat x equal to p, where f hat is given by the formula in the previous slide. The second way to estimate var for the kernel under the kernel method is to use this formula here. On the numerator, you have the sum of f hat I minus a half divided by n minus p. Then you have this. These are the same thing I talked about in the historical method. And then you have divided by this. Okay, where the data arranged in increasing order. Meaning the same thing, that is, this is the smallest, the second smallest, and this is the largest, right? So this completes the kernel method. So there are two different ways of estimating var under the kernel method. Either solve this equation for x, right? That will be the var, estimate for var, or use this formula. Okay. So this completes the four different methods for estimating var non-parametrically. Now in the next video I shall talk about semi-parametric estimation of var.